So we will start now this new session of the AstroGeo Seminar. And apart from astronomical timing, a very important record is the paleomagnetic record, because as well as the astronomical tuning, it's something that is valid all over the planet. So once you determine its age at one place, you can, if you find another record in another place, you can correlate them and get the timing. So this is extremely important for the establishment of chronology. And so we are very pleased to have here Denis Kent, who has been in Lamont all his life, basically. He told me just before that he started with sea cruise for Lamont, and that was in 1967. And Denis is really one of the leaders in paleomagnetic measurement. And he has been teaming with Paul Olsen for a very long time, and it gives a very strong way to establish the chronology of the Newark Basin. So as Paul reminded us last time. So Denis, we are very pleased now to hear you, and you can start now.
Thank you very much, Jack, and thank you very much for inviting me to give a presentation to the AstroGeo group. My discipline is I'm a paleomagnetist, and this aspect has permeated my work and throughout my research career. And it's predicated, the work sort of mostly been interested in is the imprint of the geomagnetic field in rocks. The Earth has a planetary magnetic field. It's generated in the liquid outer core. The heat engine, the cooling of the planet causes convection of the outer core fluid, and then the rotation, the spin of the planet, Coriolis forces, shapes these motions and this geodynamo into a field that's a dipole on average, a geocentric axial dipole. And so the two aspects of the planetary magnetic field that are, I think, of direct relevance to climate research and as well as the astronomical forcing of climate are the dipolar aspect of the field on average, which allows us to determine latitude in the past. And I sort of dare say, I don't think there is any other way of doing this, independent of us making some assumptions about the climate record itself, which can get circular. The other aspect is essentially the secular variation on a longer time scale, which are the polarity reversals. And so this the field for it's actually been modeled in three-dimensional models. Glatzmeyer and others of the field can make the dynamo reverse, make it, or can simulate it. But we know observationally the field does reverse aperiodically over the past on scales of hundreds of thousands and years and longer. And so it's this aspect, using the planetary magnetic field in reversals that essentially is a global signal that's nearly synchronous. That allows us to, in principle, tie in events, correlate events around the world, should we be able to recognize the same reversal. So there's an iteration going back and forth between dating the imprint of reversals and then using that imprint, that sequence, to then determine relative time, at least, or if it's calibrated, absolute time going back through geologic past. And then the yellow arrows on the side sort of depict climate coming, insolation from the sun. So this is the variation in this that we'll get to in these astronomical cycles. I won't deal very much at all with the latitudinal aspect, which is a kind of a separate interest. Right. So, whoops, sorry, getting ahead. So how do we know the field reverses? So there's a beautiful study done, over 100 years ago, where this gentleman, Bruns, measured a lava flow in some Pont Ferrand location in the, I guess in the central, somewhere in the central part of France, Central Massif. And the beautiful part of the experiment was that they also measured baked clays, clays that had been eventually cooked by the emplacement of lava, and they gave the same direction. That direction shown in that stereo net here, can you see that? Yeah, is to the south and up, the open symbol. So it was reverse magnetization, opposite to what the field is at the location today, which would be northerly and steeply down. And the fact that the magnetization, these reverse magnetizations were recorded in very different rock types with physically understood principles, strongly indicated that there was the field that was reversing, in which the lava was in place, rather than some property of the rock, given the different compositions. So that sort of was known, but not really utilized in a significant way until the 1960s. And this is a confluence of measurements made on lava flows shown on the right, this earliest time scale of Coxdale and Dalrymple. They had very few measurements. It looked like the field could have been going from reverse to normal on almost a regular basis. The idea was periodic. And this information was used by Vine and Matthews, looking at magnetic anomalies, interpreting them at different ridges, and recognizing that these anomalies could be interpreted as the lavas that on the ocean floor were magnetized in opposite polarities. And so this, combined with the Hess idea of seafloor spreading, became the part of the paradigm of seafloor spreading based strongly on polarity reversals. The polarity history quickly evolved, and our knowledge of it as more measurements were made. Like, for example, here, the Coxdale and Dalrymple scale on the left to 1964. But in many respects, the critical observation and relevant to cyclostratigraphies, I'll show in a moment, was by Dole and Dalrymple in 1966. This was a banner year for a lot of this stuff, as I'll quickly show in a few slides, who recognized that the last reversal of field was not 1 million years ago, as the scale on the left shows, but in fact was more like 700,000 years ago, and there was a short interval of reverse polarity, of a normal polarity separated by a short interval of reverse polarity. So not only was more features being discovered, but these were materially important in interpreting higher resolution magnetic anomaly profiles. And so here's one that has this famous L10 profile that Walter Pittman and Jim Hertzler published, again, 1966. And the profile on the top is from west to east, and then the other one from plotted directly below it from east to west, and she flipping it over, essentially demonstrates just a visual demonstration of symmetric seafloor spreading, that you see the same features on both sides. You notice in the model below, the black typically shows normal polarity, open bars reverse. You see the Jaramillo right there, which corresponds to this blip in all the profiles. So this level of detail became important to make a convincing case that we're looking at the reversals of the magnetic field recorded in the oceanic crust. And it's this level of detail that then allowed this profile to be used, these and other profiles to be used to chart the history of reversals of the field in a very convenient way. You just sail across a mid-ocean ridge and watch the magnetometer essentially deliver a whole magnetic profile. And you can, this was done repeatedly. In fact, there were millions of kilometers of these such profiles. One other thing is so nomenclature. Notice these numbers here. Walter Pittman did this as a graduate student. Not that that made much difference, but he took the liberty, since no one had any other idea, to just number them in a willy-nilly way, what he thought was obvious. So all these crons and now embedded in the chronology comes from this type of numbering, just looking at key features, so things that he could interpret in profile. The other key piece of information that sort of put the lock on reversals of the field is finding the same pattern, similar pattern in deep sea sediment cores, now in scales of centimeters instead of tens and hundreds of kilometers, vertical superposition. And this correspondence between magnetostratigraphy of sediments and the sea floor became the key link to try to transfer age information and polarity information from one source of geologic data to another. And so now we're getting, this sort of set the stage for cycles, Milankovitch cycles. And this soon now moving up in the 60s a little bit, more my era. Was studies in the Equatorial Pacific, which are known have these carbonate cycles that Arrhenius studied many years ago in the 1950s. But now which is blocked out to my screen because of the you folk faces on it, you can see that in the Hayes et al. Paper, there's a magnetic stratigraphy from the polarity time scales that were developed that time, that the reversal was 700,000 years before, so that there was something like 8 or 9 cycles in the course of 700,000 years. So this cyclical behavior put a periodicity associated with it. And this periodicity, the cyclicity was recognized soon after in also the continental realm, particularly in lusses that have these variations attributed to climate cycles. And so there on the right is the Luss curves that George Kukla published in 1970. And there on the left is the carbonate cycles from the Equatorial Pacific cores, same number of cycles. And they both have a magnetic stratigraphy. So this is the way of linking the two. So regardless of what the age is, it turns out the age was off by quite a bit for the Bruns-Matsuyama. The idea was that you're looking at the same reversal, links these two very disparate recording systems. And so, of course, the climate cycles, the cyclicity is global and it can be correlated. And so age information could be transferred from one medium to the other. That becomes a key feature. These cycles, speaking of age, being dramatically off, these were now going to oxygen isotope record of, I think in both cases, planktonic 4 amps. And so in the lower diagram is the curve by Emiliani, who was working on this in Caribbean cores and elsewhere, and developed that numbering system. Again, was like Walter Pittman's, just numbered the ones that looked prominent. And so that's what we have, the marine isotope stages. And he went back to about stage 17. And unfortunately, the core was quite long, 1,400 centimeters, but it didn't go through the last reversal. So his age concept, which I've tried to indicate, he had the base of this sequence, stage 17, at no more than about 400,000 years. Basically, I think he took climate theory literally and said that, eccentricity doesn't cut it, so let's use obliquity. So this is basically almost an obliquity time scale, very short. And then there was a number, Wally Broker and others did proto-actinian and other sedimentation rate estimates, But I think because it's my field, I think the convincing calibration of these cycles was in a core from the Anton-Java Plateau, VIMA 28238 shown at top, Shackleton and Updike, who number one extended these isotope stages and determined that stage 19 was at the Bruns-Amaziah boundary, then assumed to be 700,000 years. So rather than 400,000 or some number like that, these sequences are something like 600,000 based on that interpolation. So it was way off in the Emiliani. The concept was okay, the cycles, but the timing was wrong. And so didn't allow that sort of died off because it was not correct. And that led directly soon after, from 73 to 76, the well-known pacemaker paper. These three gentlemen here, Jim Hayes on the right, John Embry in the middle, and Nick Shackleton on the left, who through a series of cores in the Antarctic sector measured a variety of parameters, oxygen isotope, some planktonic forams, and then a bunch of radiolarian proxies of climate, and did power spectrum and the whole to show that there was these have clearly imprinted with the Milankovitch signature. So shown in this power spectrum, the 100K eccentricity, the obliquity, and even the precession. So this was in many respects for some of us the beginning of astrochronology in a kind of more rigorous sense. But then for the rest of us, kind of hard to mentally digest an oxygen isotope value of a planktonic foram. When you look at exposures like this, you see these and you're convinced of cyclicity. You can practically look at the whole hierarchy you expect to see. And this I think, really beautiful study that Fritz Hilgen published, essentially on sections like this, was somewhat different, but they look pretty much the same in southern Sicily. Essentially looking at a local signal carbonate contents. You can see, depending on how you average it, these are the 400K cycle, a little less averaging is the 100K cycles, and here are these couplets that essentially are the precession. So all there, very beautiful, and match very nicely to a leading order insulation curve shown on the right, based on precession and eccentricity modulation. So that actually is kind of relevant, and I still don't know how this has been resolved in general. And let me just bring this up here. When you're looking at a local lithologic signal of climate, like shown in that Sicilian sections and that Hilgen described, you see, as he showed, a full array of what you'd expect from if it was a Milankovitch forcing. So another example of that is back to where VIMA 28238 was recovered, the Anton-Java Plateau. There was an ocean drilling expedition there, and they had a site, and it's sort of a neat thing where you can get away from age calibration is measurements of oxygen isotopes and planktonic forams in practically the same samples you measure carbonate. So here's carbonate, very analogous to what Fritz Hilgen measured in the Caporcello section, and his oxygen isotopes, which measured in, for example, VIMA 28238. When you look at the power spectra of these, it's the local signal of climate, that kind of local one, that you see this characteristic Milankovitch signal. Is even a hint of a 400K in there. But the same record only shows this kind of mostly dominated by 100K. Muller and McDonald sort of seized on this as inclination. I don't have a strong opinion on this. except I think the oxygen isotope, the reason I bring this up, I think the oxygen isotope is integrating a global system, the ice volume, local temperature, and ocean circulation, so that it's a much more complicated signal, although the one that we tend to use, that's often used for cyclostratigraphy. So just a point. We get back to the local one. Actually, I bring this up because toward the latter half of the talk, we're talking about a place where there are no oxygen isotope records, i.e. in the continental. Yeah.
Excuse me, Dennis. I don't understand what is the proxy on the local. What is the local climate proxy?
It's coarse. This is coarse fraction, but it could be carbonate. Essentially, dissolution index. Sorry. So it's a measurement of looking at. It's a carbonate. There's virtually no detrital elements in it. It's sort of clay sized. And so what they're measuring, the coarse component, is essentially broken up 4 amps.
Okay.
So it's a good point. No, it's analogous to carbonate, but it's not carbonate per se. It's a sort of a character of carbonate. It's a analog. It's the look at dissolution curves, basically.
Thanks.
Yeah, please feel free to ask questions anytime. Right, so this sort of gelled into now getting into timescales, Felix's area. So this is all these various and sundry pelagic fossil zones, nanoplankton and foraminifera. People have been studying these for many years. There's oil companies love it because you can get a lot of them in a single chip. And so it's quite well developed globally. And here on the left is the polarity sequence, known basically is the same now. This is in 2005. All these been found in sections like in Capo-Rossello. The calibration from astronomical tuning is basically hasn't changed for 20 years, 15, 20 years or more. And so this is all astronomically calibrated. Just bear in mind, each of these things are drawn as a sharp line, but it takes 5,000 years for the 10,000 years for the field to reverse in different places on the Earth's surface. And so also the other thing I want to sort of show is how even these fossil zones in the ocean, which is well mixed but does have different water bodies, these zones are not the same in all over the world. Yep. Are not the same. So correlation is going to be dependent on what your idea is relative to, even just in relative timing. So these are all indexed to the polarity stratigraphy, which is soon to be instantaneous within the 5,000 year level. So that's how you can put these together. Don't worry, they've changed the names on you. You have to keep track of this stuff. Now, poor Pleistocene has been replaced by Quaternary. 500,000 years been added, but that's a bunch of committees get to do this. The Quaternary people are very powerful in the nomenclature business. So they reimposed 19th century concept. So let's go back, extending it back in time. That's why, by the way, I'll call it Cretaceous Tertiary. So forgive me, if you can call it Quaternary. So this going back in time. So again, we go back to essentially, in many respects, used up our ability to extend the reversal record usefully in sedimentary records. That's been tried, but too much a lot of variability. So instead, the ocean record was the medium that this was done in, and so here is just representative profiles. The North Pacific is always appealing because it's about twice the rate as the Atlantic. So you normally have twice the potential resolution. Pacific Antarctic is another option, although it's kind of short. I'll show you that in a couple of profiles in a moment. But the Hertzler et al., the first extended time scale, used the South Atlantic profile, which is still the one that I think is the correct one to use. And this was a masterful extrapolation. You know, there's no age dating in the ocean floor to speak of. You can't date the tholeiitic, low potassium rocks as just a few dates that were not available then. So it's using the polarity time scale developed from lavas, recognizing the pattern, and then extrapolating it back, you know, 20-fold or so. And it's pretty amazing. You know, they assumed spreading was constant in the South Atlantic for 80 million years and came up with they're within 10%. So sort of I think an argument that the South Atlantic does have a pretty irregular pattern. Doesn't mean it was constant all the way, but it ended up being, on average, reaching about the right conclusion. And so within a few years, using the magnetic polarity record interpreted from anomalies, you develop a time scale for the entire age of the ocean floor, going back to 160 million years. So here's the Hertzler scale, and then here is the part added on, the so-called M sequence that Larson and Pittman tacked on. How was it calibrated at that time? Well, I mentioned the Gauss-Gilbert boundary extrapolated here. That's how that was done. And by that time, they had ocean drilling, so the bottom hole ages were able to essentially put dates, put at least some age estimates on the beginning and the end of these, which actually turned out to be not totally crazy. But the key source of information was to use a polarity pattern that sort of repeated throughout the oceans. It became a very credible sequence, and looking for that same sequence in the sedimentary record. And so, for example, the really classic ones, the really convincing ones were the first Gubbio. So this is this interval here. This is a paper Bill Lowry and Walter Alvarez published a few years after that. First one was 1977, where these from the geologic record, these boundaries had these approximate dates, so these could be applied to the sequence from the sedimentary record, various fossils, and then used to calibrate the whole seafloor record. So that's basically how that still continues to be done. And so the next sort of improvement was to look at the magnetic anomalies, sort of going back a little bit more detail. So I mentioned that there were his magnetic lineations are now known throughout the world ocean. So we have many choices. Where do you choose to do this? North Atlantic is clear the record going back to 180 million years, sort of, but it has a very slow spreading rate, miserable anomaly pattern. So that's not really on. The Pacific is very fast spreading, goes back to the M sequence directly, as does the North Atlantic, by the way. But there's one problem: you're missing half an ocean here. It's been subducted, and so you can't. Very difficult to evaluate asymmetric spreading or have enough redundancy to convince yourself that you have a credible pattern. And so by and large, here's Pacific, Antarctic, a little messy. It's the South Atlantic. It has a continents on both sides. There's no subduction interfering in between as you have in the Pacific. So this is the one that we spent time trying to refine. And so this is in a 30 years ago now, but I don't think anyone's gone back and done more. Is looking at the South Atlantic and essentially looking at the spreading history now as a series of stage poles, the fracture zone trends, essentially are the rails of spreading, and then looking at different intervals on both sides. You can average, you can put in other data throughout the South Atlantic and other oceans. And then the calibration came through this process, like I illustrated with the Gubbio sections, the Italian, the Apennine sections, is to take each of these dots is one of the anomalies, one of the reversals bounding the anomalies actually. And so this was our attempt to try to calibrate the sequence. And so here, this is already done astronomically. That's all It's all well known. And so this was a selection of what we thought at the time were reasonable calibration, numerical calibration for the time scale, transferring information to the ocean floor. And then those are the red triangles, cubics, and then interpolating from a cubic spline, assuming spreading is kind of smooth, not herky-jerky. And it's an assumption, I think a pretty good one, and interpolating the anomalies. That's the time scale. So that's the time scale as we developed it. And I think it's still the way it's being developed now in the various updates to the time scale. Most of these are not. It's an interesting aspect that I've been thinking about. None of, like this one is, of course, these are all astronomical, but none of these others are astronomical, at least given here. So it's kind of independent from these so-called tuned and astronomical timescales. One example of how that could change is here in the Oligocene-Miocene boundary, which Nick Shackleton and colleagues in 2000 looked at in this case, magnetic susceptibility proxy of climate, did some tuning, determined the various and sundry periods, and decided that some level with this particular, it's a nanofossil, Delphix, it became extinct. The age is going older to younger, going to your right to left, at a level that should correspond, as by bias figure is taken to correspond to the Oligocene-Miocene boundary. So from the radiometric dates, the assessment of the Oligocene-Miocene boundary was 23.8. The tuning had it 23. So this was about the level of differences that have evolved in terms of calibrating this. It's astronomical in this sense, but you have to rely on basically this nanofossil being synchronous from here to, this turns out to be the so-called GSSP, which frankly, by and large, sorry, Felix, I think GSSPs are probably not the best records of most boundaries, because they're usually satisfying one fossil group and not necessarily an event. But nonetheless, that's this is a recently published astronomical timescale by Westerholz, something they call Senograd, just published not long ago, a month or two ago, 2021, or last year actually, 2020. I can't see it. And so this is in red is the astronomically tuned timescale, and it's overlain on just what I showed, how we calibrated back 25 years ago. And by and large, not shockingly, it's actually pretty close. And there's some deviations of order 1 million years. So for example, here, we use 23.8 just from a radiometric inventory, radiometric dating inventory, and the astronomical has it 1 million years, 800,000 years younger. The KT boundary, we use 65. It's now taken to be 66. So this is about the level of the differences in 25 years. But the other interesting thing, though, it's still fairly smoothly varying, suggesting South Atlantic is still not a bad place to use as a vernier. Quickly moving on to the M sequence, that sort of more or less lies fallow. People have worked on the astrochronology of some intervals, but I haven't really kept up with that very much. And so I think to many respects, this scale from 1995 is still not too bad, at least as a jumping off point. Is the most important, perhaps the most important date calibration is in the Mesozoic, I would say. Certainly in the Cretaceous is something called M0. And I'll show that in a minute why that is so important, because it anchors essentially a 30 million year stretch where there are no reversals. So we don't have a limited ability to correlate using that media. And so I go into the M sequence, which I didn't have much to say, except I want to focus a little bit on this M0, which is the bounding reverse polarity of the Cretaceous long normal, 30 million years of one polarity. And it becomes very important because essentially governs the spreading rate in the Cretaceous quiet zone, which is important for outgassing and things like that. So and this is a boundary that's bounced back and forth between about 121 to 125. And I think, I believe I took a quick look in the 2020 time scale. I think it's back to 121. So it's a yo-yo boundary. And it has to do, I think, still to do with this in the MIT GUIO, whether this reversed interval that has a date associated with it, is that M0 or M1, you know? So there's fossils involved, there's all kinds of arguments. Now we're back up to 121, which is, okay. And the reason that's important is sort of illustrated here, is that here's M0. And so here's this big stretch of normal polarity. And this boundary, Campaign and Santoni of 33, 34, that hasn't changed much, 83, 84 million years. But this one has been all over the place. And in earlier days, it was even as young as 110. And that made this crust being produced in a very short amount of time had a, like Roger and Lawson and others thought, a very large CO2 effect, or sea level, and, you know, with the expansion of the ocean floor. So this turns out to be an important boundary. It's A to date. Cyclostratigraphy has some to do with it, with trying to figure out where what the duration of the APTS and stuff like that. But I won't say more about it, but look out for this one. So that sort of takes us through the seafloor records. Let me go back here. And so the seafloor, your photos are there back to about 160 million years. It's about the age of the oldest floor. So this technique I've described, that's the limitation. You run out of ocean floor. So then the alternative is the slogging approach, section by section, using magneto, bio, cyclo-tomato-stratigraphy, and geochronology. You know, just all the different techniques, but trying to get the redundancy that we assume that inherently from all the profiles collected in the ocean floor and mechanism. Okay, but let's go back. So I'm going to go back now to the late Triassic interval that spent a fair bit of time working on with Paul Olson and others. I'm skipping over the early Jurassic, which we heard about, that we hope to hear great stuff from the JET project. Stephen Hausebo talked about that a few talks ago. So I want to say a few words here about literally a few words, because Paul has gone over a lot of this extensively, and just to sort of contrast the approach and how one might be able to learn something integrating astrochronology with the polarity time scale. Newark, you're familiar with, rift basins, opening of the Atlantic. Going to focus on the Newark. It's cyclic, so this is a kind of it could be southern Sicily, right, Paul? You know, all the cycles like Caporasello, you know, you can see it, they're there. So it has a very tangible aspect of it, no isotopes, nothing like that. You know, it's a sedimentological interpretation, but it's very thick. Here are cars, you know, this stuff goes on for thousands of meters, not all like this, but something that can be interpreted. And so this lent itself to a drilling project, series of holes, 1,000 meters or so thick across this half graben. All the stuff is there, you know, tracking is, well, Paul has done this extensively. I've gone along a few of these. You can trace these beds, and so you can find some stream or parking lot where these things are exposed. But it's a matter of seeing it in superposition, which coring does. And so these are These are can be linked by these characteristic beds. And so here's a few aspects that I think are important to at least convince our colleagues that that these continental sediments can be complete. You know, how do we know? Well, you can look at two cores that independently linked by this member that named the Perkasie, characteristics of black shale at the base. And here, two holes 40 kilometers, 42 kilometers apart. And here's the cyclostratigraphy Paul described and others. And here's the polarity stratigraphy that we developed in the cores. And so you have a beautiful correspondence from this spot here between the cycles and the polarity stratigraphy. It looks like they're both timelines, you know, and so this is what we paid a lot of attention to in these overlaps to show we have completeness and they both acting as timelines. And so here's the composite series of holes, 10, 20% overlap in all cases, satisfying the constraints that were available, and then some cores up here, 4,000 or 5,000 meters of section. And the problem we're using biostratigraphy in this case, you have pollen, if the odd concostracan, is there's only about 4 or 5 biozones. So each of these, you know, anomalies, the late Triassic, 25, 30 million years, you only have resolution at the level of the Pleistocene boundary, not that interesting. But we have a lot of polarity zones, and we have this depth ranking of climate as a climate proxy, and we have excellent lateral consistencies suggesting that this might mean something. So here's an idea. I mean, it's just this talking about the cyclicity in a rudimentary power spectrum sense, no tuning. This is looking at the Lakaton, is very large amplitude changes between deep lake and no lake, and looking at this interval in Paul's depth ranking and power spectra, looking at this and then looking at the power spectra using even just the most general time constraints. It looks like the most plausible interpretation, which will show is verified, is that we have the 400,000 year cycle, a couple 100,000 year cycle, and then this mush of poorly resolved precession cycles, which looks very similar by analogy with the record, just calculated record from the last few million years. So that's the conceptual idea. And so this record is then interpreted in an analogous way that Paul described last time. The geochronology comes in and can only come in this one place because it's the only place to date things. And that's in the lavas of the Camp Central Atlantic Magmatic Province at the top of this and near the top of the Newark section. And these have been dated just beautifully by Sam Bowring's lab, Tim Blackburn. Whoops, all right. And so this shows a couple of things. First of all, it provides an anchor. These are very tightly constrained dates. And notice that there are three lavas with interbedded sediments that Paul and colleagues have interpreted as cyclostratigraphy and could determine the relative ages of these lavas. And that astrochronology indicated 600,000 year interval for these lavas, and the uranium lead, the zircon badolite dates had 604. So this was a really important characterization, important constraint that what was being viewed was in fact Milankovitch and was recorded properly. So we had an anchor, first order verification that these other cycles might be similarly. For the anchor, more specifically, just translated down to a little short polarity interval, E23R, just below the basalts, which is found in a variety of other basins, Argana, Fundy Basin up in Canada. So 201.6, extrapolating this date down, assuming there's a precession cycle in between. And so this is the time scale, basically. It's here's the anchor we just talked about. And these little squares, each of these is what's so-called McLaughlin cycle, or 400,000 year, 405,000 year cycle, going back to the base of the cyclic section, extrapolated back for in the fluvial section. 150 meters per million year on the average sedimentation rate. And so this is astrochronology here, uranium-lead geochronology here, and with the polarity reversals I show you in a minute. So this is the Newark record, but I want to add on the Hartford Basin because it has some important aspect to it and sort of creates the sandwich over the camp. And so the Hartford and Newark Basin are very closely correlated. They each have these 3 lava flow sequences in them. Here's the interbedded sediments we just mentioned, that it's 600,000 years between them. But what Hartford has is this couple thousand meters above the basalts that is cyclic, and we've also developed a polarity stratigraphy. And here we have the first order connection with the marine realm, and this is shown by dates. These additional dates are sort of not sort of, but they suggest that the geochronology or the astrochronology is correct. So on your right, hidden from me, is the Hartford record, shown here with the polarity stratigraphy and the cycles that interpreted from the sediment lithologies. And on the left is in St. Audrey's Bay and essentially St. Audrey's Bay, and with cyclicity, polarity stratigraphy, and dates that could be tied into it via bias stratigraphic constraints. Some of these are from Peru. And so, and so what this shows is that cyclicity, I mean, you get this correspondence between the non-marine and the marine. It's 1,000 meters per million years, a meter per 1,000 years sedimentation. It's ripping, but it's all being recorded, and because it corresponds very tightly to these sections, which are much more condensed, but they're marine. They have other, like carbon isotopes and other things that are interesting. So this gives credibility to the cyclostratigraphy up here. I just talked about the dating here. So transferring thicknesses to time essentially via these McLaughlin cycles. And this is a dangling, but still is a dangling chronology. So we know we have dates in the Jurassic part, but there are no dates down here. So this is completely based on astrochronology and with the polarity signature that we can use to try to test it, which is what we proceeded to do. And the reason that this really came up is the marine people don't really like this idea of completeness in the Newark, I guess, and suggested, various authors have suggested that there's 2, 3 or more million years, 5 million years here, 5 million years missing in the Newark. And so the implication of that is in the last time scale is it's kind of a hedge move here, right? Jim is here having a break, but then here he has it okay. But it's kind of a specious argument because the region, in terms of the duration, because the base of the region hasn't been defined. Remember, we have to rely on committees to sort of bless these things, and this hasn't been blessed. So there's different concepts of region, just like there are different concepts of quaternary, depending on which volume you read. So, but in terms of the non-marine fossils, this is a pretty unambiguous call. Because of this Konkostrican bias stratigraphy, there's supposed to be essentially a 3-4 million year hiatus in the Newark. The importance of that is, going back to this, is that, remember, this whole chronology is suspended from here. So if there's a break in there, you have to add some indeterminate amount of time to all these reversals and as well as the cycles. So this became a motivation to go and better get a date down there. And there are none in the Newark. But out here in the Colorado Plateau, there's plenty of uranium lead dates in the Chinle Formation, which the Newark sequence broadly corresponds to. And so this became the venue for the Colorado Plateau Coring Project. Just briefly highlight what this one test is. So drilled here on this on Chindi Point, recovered something like 500 meters of mainly, well, 400 meters of Chinle. There's some Molencopy here, which I won't say anything about. Keep your eye on this. This is not snow. This is something called a black forest bed. And we knew this is likely to work out because this black forest bed has been dated before. It was zircon geochronology. I think it was the first, I believe it was the first uranium lead dating in the Chinle. So there was a number of efforts on this. So we had a pretty good idea this was going to work. And the site was cited just to go through this to make sure, we get the one thing that we were very sure was going to work. So here's the initial result from that exercise. So here's the core. This is a Cenozoic unit here overlying this. So this is the Chinle. This is the polarity stratigraphy as best as we could develop from that core. These are the polarity designations we made. And this is our effort to correlate it to the Newark, assuming this is the template and complete. So this is, this is a set of assumptions that we made. And these are the dates that go along with this, with the astro scale and the Newark, assuming it was complete. So this is the null hypothesis is it's complete. And so therefore it makes a prediction of what this age is of here's the black forest bed here. So this makes a prediction should be something like 210. That's the idea. And it turned out to be 210, or darn close to it. Plus there's some other uranium lead dates that Roland Mundial and Connie Rasmussen produced. Low in the core, there's some outcrop work that's also shown here. And so this is in the upper part of the Chinle, this has very good agreement. So essentially the prediction is verified very closely within the areas by these additional measurements. The uranium lead dating is not trivial in many respects, the precision, keeping clean labs and stuff like that. But it's also in a more general way not trivial because these are detrital zircons. And so you can see the populations here. Each of these are now with the chemical abrasion thermal ionization mass spectrometry, the really precise and accurate method of measurement. These are individual zircons with their error, with their ages, and I think they use 2 sigma errors. And the problem you see is you have to make choices. Somebody about what the date is, because here, for example, is the black forest bed, I think, yes. And so that date of 210 comes from the congruence of a series of these measurements, which give you the number that's quoted there. But notice there's a number of zircons that have to be rejected, these because they were detrital, they're older. But even this one, which is younger, and that implies there was lead loss. So it'd be nice to have it just one-sided and take out the detrital, but that's not the way nature works. So this is a choice saying we don't know what this is. Maybe the lattice has been busted up and the lead just sort of evaporated out of there, which is basically we're not being too specious is how that's been interpreted. So anyway, this works well given these choices by the people who do this. But notice here that there's some dates that start flying off. This is from outcrop that don't quite fit don't fit the story, suggest there's a nonconformity or some problem here. We published this before we finished the rest of the section, fortunately. It's sort of, so this the other motivation besides saying that the Newark is complete is suggest that the 405K term, which is the Newark is based on, is also looks pretty robust going back beyond computation space. So we finished the rest of the core, only a couple slides left. We finished the rest of the core, and here's what we found. So this is the part that I just showed moments ago. And then here is that date that sort of was a stray, but here's a bunch of other, these are all outcrop dates. They're off what would be our preferred interpretation of the core magnetics, now completed to the template from the Newark. Notice, I would also point out that before I go on, that Steiner and Lucas actually did a pretty good job from outcrop in the sections that they measure. They correspond great. If they just gone a little bit further, they would have gone across the Black Forest bed, and with that date, they would have said Eureka, the Newark is okay, but they missed 100 meters a section because you have to go laterally, and it's very hard to correlate these. That was the reason for drilling. But then this part here, this essentially attaches to there. This better matches this interval here. So the other point is that the core is not some unusual facies or something. The broader, these go across practically the whole part, are saying the same picture. But what's this all about? Well, I mentioned these are an outcrop, but Connie and Roland did this work, finished looking at samples in the core. And it's a complicated diagram, and I won't go through it, but again, keep your eye, and you look at some of these things, these are the ages here, and each of these are zircons. There may be alternative interpretations, and you got to do something to get rid of data. You got to do something because there's a spread. You can do the average, but then I'll show you, you might as well just, why bother with the precise one? You might as well just use the laser ablation provenance studies, in my opinion. So here it is, here we are. So this is, I showed you again, the polarity stratigraphy here, and now these are only samples based on the core, all the outcrop ones, basically all out here too, but the core ones join them as well. And this is the polarity interpretation, the preferred one. And these are out here, but there's always seems to be the stray younger zircon that actually fits the model. So this is kind of encouraging. Maybe these are detrital. The difficulty is, here's a stray young one, and here's a stray young one I mentioned earlier. These are way off the mark. You have to have special pleating. And I think something needs to be done about developing techniques to really differentiate those that have lead loss from truly young ones, because I think this is a kind of a subjective problem. So what I think there's another indication that these are affected by contamination by detrital zircons, despite best efforts to try to eliminate them, inspection, looking at doubled. And that's in the laser ablation. So this is a technique you can blast through a lot of samples, a lot of zircons, and you get populations, which is illustrated here. Forget these are older ones. Just let's focus on those that are in the range of the Triassic. And so here we are at the base of the Chinle and going up. And remember, this just to remind you the break in the where the zircons. Let me just show you. This is important. Remember, so this is in the mid-Suncella, this unit where the down to there, everything seems to work together. But here below that, something goes awry, the dates. So there's either an unconformity or some process of emplacing those zircons is different. And so if we look at the laser ablation populations, what catches my eye, and I put this line in, Georgian put this line in, I put it in, this one vertical, it sure looks that going from almost the base of the Chinle right up to the cincella, there's really no significant difference in population age. They have the same mode. And it's only when you get through the middle cincella, you see a drift getting younger, which you expect from sedimentation, getting younger as you go up section. So I think this is another indication that most of the zircons down in this lower part of the section are reworked. Essentially, we're reworking something that's about 220 million years old, and it gets recycled up, and that dominates the population. The odd one, there are younger ones in there, but boy, it's lucky you hit them, and then you're not sure if you're looking at a lead loss issue. And it's only when you get through the middle of cincella, it starts getting younger. The other clue that this is reworking is this one sample right here. This sample you could put this sample down here and look the same in terms of its population. So this is just happened to be a stream sort of wandered over there that brought the same population of reworked zircons here, whereas otherwise there were juvenile ones being delivered from whatever the source volcanoes might be. So that's the caveat about using uranium lead dates. It could be very precise, but you could be precisely misleading. So this is, again, just finishing up on this topic, this is from George's paper. Everybody plots things differently here. Ages are getting older to the right before to the left. So here's the magnetic interpretation I showed, this dashed line. Here's again, I put this overlay on it. These are all the dates that now include the outcrop ones. The outcrop ones and the core ones are not doing anything materially different, is from my perspective. These are all reworked, or not all, dominated by reworked, with the odd one the odd young one that seems to fit this pattern that sort of makes us want to interpret the simple magnetic linear pattern as being real. And then it's only when you get up here that you start getting congruence. So that's the uranium lead zircon story. So it doesn't matter how accurately you can measure these things necessarily. It's where they come from and on subsidiary effects like being detrital and having lead loss. Lead loss, I think, is the killer because it now becomes a two-way problem. So wrapping up, going to this other approach, the stratigraphic approach, the one sort of focused on the Newark-Hartford, I think through using an integrated approach where you get dates, you need dates that you can, but in this case, go into the Chinle, show that the Newark implies the Newark is complete to better than a fraction of a 400,000 year cycle, going back to at least 215 million years. Who knows what the lower part? There could be nonconformity there, but doesn't necessarily mean the cycles are wrong. You can truncate a cyclic series almost anywhere, and you still probably get the same power spectrum. So nonetheless, it looks like the null hypothesis that the Newark denominated in a 400,000 year cycle, that looks like it's justified. And in terms of further work, there's a long gap between the M sequence and the Newark in the early middle Jurassic. This is what the JET project is addressing. It would be great to have that for a variety of reasons. But there's also an interesting gap in the Carnian that sort of still needs to be filled in, essentially between the base of the Newark, which is shown here, and correlated to the Pizza Mondella, which I didn't have time to say anything about. It's a pelagic limestone. It's a limestone sequence, quite thick, and it has just above a date, the only date that sort of exists down in the marine realm that's precise. And then then when you get into Ladinian, these dates like the Latimar, places like that, which have good dates. So there's like a 5-6 million year gap that's not really well represented by good stratigraphic sections, certainly not with good cyclostratigraphy. There's some efforts to plug that in, but they're sort of floating right now. So there's a few things to do. And there's also the venue of the Carnian pluvial, so something even more fun to look at. That's it. Thanks.
So thanks a lot, Denis, and thanks a lot for this very broad history of the problem. It seems that you started basically with the expansion of paleomagnetic measurements. So you have basically lived all of it in some sense. And thank you also for this very detailed analysis of the Colorado Plateau measurement and the relation with the Newark Basin, and showing us that it is not as simple as one could think by just looking from far away. So, and that there are still plenty of problems. So now we have time for question, continuing on that. So everybody is free to ask question, but just raise your hand if you can. It's in reaction. The hand is in reaction. You have the small hand which you can raise, and it will be better to do that.
I have a question.
Yes, Felix.
Dennis, thank you very much. Brilliant. I much enjoyed it. Very elementary and profound. I mean, to increase your unpopularity record, which I said is non-existent, I was thinking that since you gave a stab at the global boundary stratigraphy and boundary effort to establish gold spikes in sections, I thought that you kind of are hovering around the issue that, of course, the Lamont, the Newark section is so brilliant that you could extend the boundary concept in the non-marine record and establish the base of the Radian and the base of the Norian in your section. You'll become very unpopular and you get lots of people following you and shouting at you, but you certainly will get attention. I promise you that. What do you think of that?
Yeah, no, that's a fair point. I guess I was trying to be a little provocative in these. I've been on a number of these GSSP committees, and I loved them. I went to great places, saw great sections, had great discussions.
Right.
But in the end, it was not in the end, but it tends to be, as I think you know. You can give an opinion. It tends to be dominated by certain fossil groups, and so, for example, in this this is a long-winded explanation, but forgive me. But like, for example, the Triassic-Jurassic boundary, it's up in some mountain in an upside-down section that has no magnetics. It's been metamorphosed, but because some ammonite rolled out of the cliff, people say hallelujah, and when you hear ammonite, it's supposed to tell you something. So there's a couple of difficulties with these sections. The other one, and then on top of it, it's I would, again, to be more unpopular, is to call them immaculate conception. And so the boundaries, there's nothing happening there except a fossil showed up. So let's say the Permo-Triassic, the major extinction, all that. Well, that's not the boundary. People think it is, but it's some conodon, right? Some conodon crawled into the section, part of it. Who cares? No, really, because and so I'm being I'm taking a liberty of being in a group, there's a little different, and so I'm now willing. I'm not that enthusiastic about making the non-marine go through the same route, because what are you going to get? Some concostracan? The region going to be some pollen that, something that, and the continent happened to be at 10 degrees north. So you get, Paul, no, I don't know, pick some taxa but the one in Norway in the basin is going to be different. And so we'll be arguing continually about this. So I'm not that enthusiastic about it, I guess. I think these are worth discussion for correlation, but to make those the boundary based on that criteria may not be the best way to learn about Earth history.
I appreciate what you're saying, but for example, in China, with the non-marine records in the Cretaceous, they're trying to do formal chronostratigraphy in non-marine records, and they want to kind of make sure that the states, let's say the Santonian or the Campanian, is there, and they use whatever it takes to do correlation. So in your case, I mean, it's simply philosophically an issue of extending the marine formal stratigraphy to the non-marine formal stratigraphy.
Well, there were moves afoot to make the polarity stratigraphy have type sections. Years ago, there were discussions about this, which I think would have been a disaster. And well, because the marine record, I'm sort of wedded to the idea of the type section. To me, is the marine anomaly record, but it's processed. It's not any particular. If you make it one particular profile, which is the equivalent, then it may not be right, or you may not have means of correlation to it that are adequate. So I'm not sure. I think the marine in the magnetics realm, I think, has prospered because they were not tied to GSSPs. That's one opinion. I think having one there's some uses to it, but I'm not sure if where you weigh the benefits. It's worth open discussion. It's not a no. I mean, I'm not. I don't typically use them.
Oh, well, thank you. I don't want to go further. People will get bored by this formality. But thank you very much.
Any other question? I have one, which is about what is the accuracy to which you can measure the transition in the paleomagnetic reversal. What is the limitation? What is the absolute limitation of this accuracy? What would be what can be improved?
Whoops. I'm showing you how to do this. Hold on a second. I can't get the slide right now. It's just the transition duration is pretty well known. There are records in about 5,000 years.
When you mean that is well known, you mean by simulation?
No. Simulation is a simulation. You can make it almost anything you want. I mean, they don't know some values.
The observation.
No, observation. You look at very high resolution, high deposition rate sediments.
Yes.
And people have measured them in, literally like half a centimeter scale, and look at how long, what the recording is. So it's a convolution, the recording, the field. But I think doing this, this has been done, is something of the order of 5,000 years. There's some latitude dependence, which is interesting. It's shorter near the equator, longer at higher latitudes, maybe because the nucleation of a reversal could starts at the equator and then migrates to higher latitudes, for example, so you don't see it there. But something of the order of 5,000 years is now particular ones. If you want to know that I mean, how is that? Do you have a reason for thinking it should be more or less?
No, I just, so that's one answer. But if you have something that lasts 5,000 years, you may even get an accuracy that is shorter than that. If it were, for example, if it were always the same, if it were modelized, and you can think that, for example, the middle of it, or can be constrained to an age that is with a higher accuracy than the time it takes to make the whole reversal. So what will be important would be then to know what is the variation from one reversal to another one with respect to this 5,000 years.
Can you see this?
Yes.
Is it projecting? So here's, I think directly to your question, as far as I know, this is amongst the best evidence. So what you see, this is stratigraphy. These are values and of a particular reversal. And so what's now comes the interpretation. This is the part that's the transition. So you have reverse polarity here, normal polarity here, and these are kind of indeterminate. That becomes a transition. So there's a lot of groups that have looked at what happens during this time and the paths that is followed. But here's a straightforward estimate. And so here there's some 30 of these for different reversals, mostly the Bruins and the younger ones. And so what you see, this is thousands of years. Where's that date come from? That sedimentation rate. Each of them is arguable. You can look at it, maybe refine that. That's probably as much of a variable as any, because you're doing sedimentation rate at a short interval, and you may have been calculating it from let's say the whole Bruins and how that translates. This could probably be done better with cycles. If you think you have like the Bruins-Matsuyama is stage 19. We have some idea from astrochronology how long that is. You can do interval wise. So you can improve this. Actually, that wouldn't be a bad idea for someone to do. But here, such as it is, here they are. And I mentioned, so a couple thousand years at low latitude, longer at high latitude. Maybe it could be simulated essentially like an octopole reversal phenomenon, but it could be some artifact too. It's worth exploring. It's of order thousands of years.
Okay, yes, that slide gives a perfect answer to my question. Thanks. Christian? We don't hear you, Christian. Oh, yeah.
Now that should work.
Yeah,
you presented a series of uranium lead dates with some outliers to the young end and to the old end. Did I understand that correct? Although these exist, your interpretation has a clear preference for one of these paths, or is there an interpretation problem as well? So my preference is the one that agrees with the magnetic polarity stratigraphy. I'm only being half facetious. It's the young one that bothers me. That whether it's the temptation is to go to the young one as the one that's least likely to be tridal, but then there's these examples that are just not, they're not realistic, like the one at the Black Forest Tuff, if not Tuff, the Black Forest bed. That Paul and I, when we first saw that from Roland, was it 203, Paul?
Yeah.
I mean, it was just it would just change everything. I mean, it was so beyond that it's just not.
And it was one crystal.
One crystal, right? Not plausible. So I think the spread. I'm not the one interpreting the uranium lead dates. These are interpreted, although we have discussions with them. What's plausible and what's not. It's not a set procedure. There's some set procedures, but the outcome may allow other alternatives, as in the case of rejecting the 203, that young one for a 210. Now, if you include that in, all of a sudden your errors go up. Maybe it's part of your error package. And that's why this realism about how the precision and accuracy issue of what you're measuring gets involved. No. Can I show this? I don't know if I can say this. This may be a little bit related. Can you see this? Mm-hmm. Okay, here's dates. This is not uranium lead dating, but just showing for the last reversal. I think this also goes to the issue of that Jacques asked, what do we know? How long does it take? And so here's a case where the transition, here's it takes less than 5,000 years, making estimate of what's been measured, without getting to this. This is this band shown here. So here's two good groups looking at the same reversal. The best dated one's got to be, it's the youngest, least complicated. It's got microtektites down here and play, it's just boxed in, stage 19, and there's 10,000 years difference. So here's Chinle, I think Brad Singer's on this, Dave Hodel, people, all serious people on both sides. That's just, I think, reflects the uncertainty. There's inherent uncertainty. We don't know everything. And so here they put the Bruns-Matsiema boundary, Matsiema-Bruns boundary at 770 something. And here they put it at 773 versus 783. Looking at the same boundary, not in the same core. There's a couple of variables in here, but so the reality, I think it was Jacques, as your question, how long does it take? I think these other uncertainties, it doesn't, I would say you can't correlate to better than half a precession cycle. Now, my God, just looking at these things, 5,000–10,000 years that are legitimately been argued about. You can take sides on it, but you can't easily eliminate the alternative. So this is not quite the question you're asking, but I think there are choices to be, that are being made and what data to select, and one fits one's prejudices or other information or not that you're stuck with.
Okay.
Yeah, thanks a lot.
And Paul,
yeah,
a question?
Yeah, sure. So I just in the publications that dealt with the uranium lead dating, the Rasmussen et al. Papers, it's worth mentioning that they had two hypotheses. One in which they used a kind of algorithmic approach to select the grains that they used for their preferred dates, which basically was to use the youngest coherent cluster of uranium lead ages on crystals for chemical abrasion ID10s. And that does not get rid of course, the possibility that those grains are recycled from older strata. Then the alternative model tended to use the younger grains from the same sample. Then they tended, for the part where there was any discrepancy at all, to fit the paleomagnetic model. But the problem with that, of course, is you still, as Dennis said, have these younger grains, which there's no objective criteria for excluding except that they don't fit your model. So we still have that issue, but the beauty of, we don't have to rest at that point, because historically, because of the way the Black Forest bed was dated, and with great success, that was a sandstone. It was recognized at the very onset that these were detrital grains in a sandstone. So then thereafter, including for our project, the preferred sample was from a sandstone. Well, sandstones are all fluvial. They're all to some extent recycled. And this question is, did it happen to sample young ashes somewhere? You can take that a step further and say, well, if the young ages that we're going to use for our model are actually from airfall, we should be looking at the muds, not the sandstone, because the muds should be dominated by the airfall rather than the recycled grains. That experiment has not been done. We have some preliminary experiments in the works that suggest that the muds are in fact tend to be dominated by airfall, and then if you have a sandstone right next to a mud, the sand is dominated by recycled grains and the muds are dominated by the airfall. But the muds are bioturbated, and so you don't see the airfalls. They are what are called in the Cenozoic and especially in the Holocene, cryptotephras. because the bioturbation process has mixed them into the sediment, so you don't see them as discrete airfalls. So that hypothesis of using the muds instead of the sands has yet to be fully explored, but it's a potential way out of this problem. You don't have to just say, oh, we don't know what to do, we can't decide what's recycled, what's not. You can actually do some more experiments. And to on a completely different subject, Dennis, of course, since it's your work, you know that we have you really sampled the polarity reversals in the Newark very finely, and we can see that they are within one single precession cycle, the transition. So that's a completely independent measurement of the amount of time through the transition, if you believe the sediments are recording the polarity stratigraphy, polarity properly. That's all I wanted to comment on.
Do you have, Denise, do you have comments on what Paul just said? Or?
Yeah, I think this idea of sampling mudstones is a good one for all the reasons that Paul mentioned. I don't think what I'm curious to know, I don't know, is whether that will address the young zircons, and what I think that will help address the detrital one. But somehow I don't think that's that's a problem. But the technique has been successful dealing with it, looking at the youngest ones, but then it's the youngest one argument that is the deficient one, in my opinion, that if something could be developed to determine whether those particular grains are, say, have lattice defects, I don't know, it's why, are these grains, why do they lose lead? There may be some ways of determining that. So that would be my one caveat. I totally agree. It'll minimize the detrital, but it'd be interesting to see. Maybe it'll also, address this younger.
It won't get rid of the younger ones. That's going to require, as you say, Dennis, a different technique. What the MIT group might say is you just have to have them etched. You have to have them soaking in the HF longer. The problem is you can get rid of all the grains and you have nothing to look at. So but that 203 data in the Black Forest bed might have gone away if the temperature in the HF bath was higher or the amount of time was higher. But then again, then maybe they all would go away. So I think a separate technique is needed.
Yeah. Just one final is that an interesting thing is the way the MIT lab has done it. And the way Roland's lab has done it is that Roland, I think, has relied on the laser ablation populations and selected from those. They're done on the same grains. I guess you make a pit and then you can grab it. But they tend to select the youngest ones, for kind of obvious reasons. The MIT group does, as far as I could tell from the literature, doesn't use that selection criteria. But in their populations, they rarely have the young ones, or they're less frequent, in the display. So they're using some visual or other characteristic, the character of the crystal, some other property that allows them to eliminate those, which is interesting. That'd be interesting for that group, for that community to sort that out.
That's correct. I have asked that question specifically of Jahan Ramazani, who was the person who actually did the selection. And they use a visual criterion. Now you can imagine how that could bias you towards the recycled grains. If there's some particularly attractive set of grains that just gets recycled and recycled and recycled, you'll keep choosing those over and over again.
Yeah.
And I suspect that's exactly what happened with these ages.
The old ones, yeah.
And so the airfall ones, unsurprisingly, might be in those sandstones a small percentage of the grains. They might not be the most attractive looking ones.
I think Matthias had a question.
Yeah.
Matthias?
Yeah, first of all, thanks for the nice overview, and I'm really enjoying the uranium lead discussion. And just from a carbonate perspective, I know some people just dissolve tons of carbonates and also hope to find volcanic zircons. But my question was more general to Dennis. What about Paleozoic and earlier? Do you think from your experience to come to magnetostrat is just more work to be done, or the record is just not preserved enough and we probably never have a very useful magnetostratigraphy to work with?
Oh, I'm not that pessimistic about that. I think there are there are many opportunities to do that. With the caveat is the caveat would a first order one from polarity stratigraphy is the Kayman. So it's another interval like 30 million years where it doesn't reverse, late Carboniferous, early Permian, which is a little unfortunate because that's the last ice age. So to look at some climatological details is polarity stratigraphy is not because there are no reversals, or not that we know about, but the Devonian, and I think there's a section somewhere like Paul. What about I never been there. The Caithness, isn't that a Devonian?
Oh, the Caithness is potentially fantastic.
And, yeah, so
it looks like the Newark. It's quite thick.
I think the trick is to look for things like this. I haven't seen, but what I heard description is something that's likely to work. And as opposed to another strategy would be do piecemeal here and there. And I'm less enthusiastic about that because that relies on the correlation, whatever you're using to put the whole thing together. And I like Steno. I really like Steno. Superposition just trumps our knowledge of time, has the arrow of time.
Okay, so be optimistic for the future.
I think there is, especially if there's a problem, that can be addressed. Find something. But it's a little unfortunate the way things work is that just when you have the late Paleozoic glaciation, that seems to be mostly in just one polarity. So that's not going to address that problem.
Just a question about that. When you say that there is no reversal, that for 30 million years, it's always the same polarity, is that because people have not looked enough, or people are sure that there has not been any transition and which is not seen?
Let's see if I can quickly. No, I think for the Cretaceous, I think there are no. For the Cretaceous, I think it's clear that there are few, if any, reversals, and there's a whole kind of analysis of this that I wish I left it in, but there are reversal frequency regimes. I can send a paper about this. Is that so that in the late? Wait a minute. Wait. You got a drift of this, I think. Most of you know this, but here. So just looking at this representation here, the reversal frequency here going back to anomaly 13, C13, is about twice as high as here. But over these intervals, it's actually stationary. There's this whole analysis that shows that. So that it's like there's intervals of 30 million years or so where the reversal rate seems to be going on at some rate, and then you get to another rate. And it's not because you're missing record, because the something called the gamma index, and you're looking at the distribution, the polarity intervals stays about the same. So in other words, it's an exponential distribution. You have a lot of short ones, fewer long ones, and it's like you can say the probability reversal stays constant. It's like flipping a coin. You just keep flipping, the probability is the same. But if you do the sequence, you'll get all different. You get all different. You get a you get a more complicated pattern. And then the M sequence is somewhere in between the reversal frequency of the early Cenozoic and the latest Cenozoic. And that brings us to the Cretaceous quiet zone. That's this interval right here, 30-ish, without getting, anal about it. It's long. And it's about the duration of these. Well, if you take 33R and go back to M3 and you look at this, you're very close. You're very close to having a same kind of distribution as either before, early or later, because it's just longer. And all you need is one. That's actually what the interesting motivation on. If you find a reversed interval anywhere in here, it's going to be almost, I think it's going to be exactly the same as before after, because once you have one, when you have one, you find a short interval, and then you have three, right? And it changes the distribution in just enough of, it could do it in just enough of a way. So the answer is a long-winded, I don't think these are because of lack of detection. I think they're intrinsic. The other, finally, the last indication we have of this, we had a cruise we've yet to publish of looking at, we had drones flying over the Southwest Pacific in a very fast spreading region to look at this interval here, about 10 million years worth, estimating. And so we could look at the, had a cesium vapor magnetometer and just ran lines back and forth while the ship went along. We had a swath map, so we knew the bathymetry, we could do the modeling and all this other stuff, and no reversals in this interval. So in a very confined interval, there were no lineations that could be interpreted as reversal. And I think there's other indications that people, I think Lisa Tokes in a group studied in the Gubbio, in the Apennines, intervals of 5-10 million years, with known biostratigraphy, and looked at them and didn't see any. So I think there's a lot of indications these are real features. It doesn't mean that there's not the odd reversal, which would be nice, say in the Kiamat or something, just to have a marker worth looking for. But to my knowledge, is not a good example of that yet.
Okay, thanks for this answer, which is very clear. Is there any other question? Okay, I think that we are done. We had but I had still a little bit a question about your first part. How do you see the evolution of the whole field of paleomagnetism, since, as I was saying, you started from the beginning, basically. And so you can also remember what were your perspective at the time and compare it to what you can think now. So what will be your general feeling about the field?
Where the subject is going, is, I think, is what you're saying. Well, I think if you have good opportunities to learn something about the field, and that's actually the way I looked at the Newark, is to look at a reversal sequence, which then lent itself to addressing a whole variety of things like, try to discuss here. And there's other times when there's a specific problem. It's if there's something to correlate, you can do this with increasing precision, with applying dates, but you need a reason for it. I mean, there's
yeah, I understand. You need to have an objective problem, and then then progress will come. Just because people will get motivated, then they will try to get the best resolution. They will try to get the best data, but you need to have a physical problem to be motivated.
And the place I'm most excited about, lately, is the combination of latitudes and correlation, reversals. because continents move. And so all these biostratigraphic, is essentially, we've been using biostratigraphy to tell time and to correlate. But I think we should turn it around, because life is the most interesting thing. And so to be able to put things in their temporal and spatial context, which I think, paleomagnetism has a big contribution to make, especially latitude. You can do all the relative motions of continents, but it doesn't tell you latitude. And so it's latitude that, it's our relation to the sun and, the whole climate system. So I think there's opportunities there, essentially turn the problem around and have not do biostratigraphy, do more biology, or, what there's proper terms for it, looking at more of the ecology and of systems. So I see that's in any time frame.
Okay, so we see that there is still some work to do, and so thanks a lot, and thanks for everybody who has stayed all along. And so that's, we'll see if we plan one more seminar before the summer, maybe. And I remind you, if you have good suggestions, to forward them to me. Okay, so thanks to everybody, and thanks again, Denise.
Thanks very much for listening. Bye-bye.
Bye.